Right now, as you read these words, you're surrounded by what might be the most mysterious substance in the universe: space itself. You probably think of the space around you as empty, as nothingness, as the absence of things rather than a thing itself. But prepare to have your reality shattered, because space isn't empty at all. It's not nothing. It's actually made of something so strange, so active, and so fundamental that it challenges every assumption you've ever had about the nature of existence itself. The space in this room contains more energy than all the matter in the observable universe. It is bubbling with virtual particles that pop into existence and vanish faster than light can travel the width of an atom. It's curved by gravity, stretched by cosmic expansion, and permeated by fields that extend to the edges of reality. Space isn't the stage where the cosmic drama unfolds. It is the cosmic drama, the most active and dynamic component of everything that exists. Modern physics has discovered that asking, "What is space made of?" is like asking what reality itself is constructed from. Space isn't made of something. Space is the something from which everything else emerges. Matter, energy, time, and even consciousness might all be different manifestations of the underlying structure of space itself. We're not living in space. We're living as temporary patterns in the fabric of space. The journey to understanding space's true nature represents one of humanity's greatest intellectual adventures, overturning centuries of assumptions and revealing that reality operates in ways so bizarre they seem like science fiction. Ancient philosophers imagined space as an infinite void, a container that held objects but had no properties of its own. Newton conceived space as absolute and unchanging, providing a fixed reference frame for cosmic events. But Einstein shattered these comfortable assumptions by revealing that space and time are woven together into a dynamic fabric called spacetime that bends, twists, and curves in response to matter and energy. This wasn't just a new theory about space. It was a complete revolution in how we understand the relationship between space, matter, and reality itself. The revelations didn't stop with Einstein. Quantum mechanics discovered that space at the smallest scales is anything but empty. It is a roiling sea of quantum fluctuations where virtual particles appear and disappear in accordance with Heisenberg's uncertainty principle. The quantum vacuum contains infinite energy density, creating what physicists call zero-point energy that pervades every cubic centimeter of space. Recent discoveries have made space even more mysterious. Dark energy, which comprises 68% of the universe's total content, appears to be a property of space itself, energy that increases as space expands, driving the accelerating expansion of the cosmos. This means that space isn't just the arena where cosmic evolution occurs. It's the primary driver of cosmic evolution itself. String theory suggests that space might have additional dimensions beyond our familiar three, with fundamental particles being vibrations in these higher dimensional spaces. Loop quantum gravity proposes that space itself might be quantized, composed of discrete units at the Planck scale that combine to create the appearance of smooth geometry at larger scales. But perhaps the most mind-bending possibility is that space is made of information, pure mathematical information that creates the appearance of three-dimensional reality through holographic projection from lower dimensional boundaries. In this view, asking what space is made of is like asking what a computer program is made of. The answer involves information processing rather than physical substances. The implications extend far beyond physics into questions about consciousness, reality, and existence itself. If space is the fundamental substrate from which everything emerges, then understanding space's nature might be the key to understanding consciousness, identity, and the deepest questions about why anything exists at all. Recent experiments have begun probing space's structure directly through gravitational wave observations that detect distortions in spacetime itself. quantum experiments that manipulate vacuum fluctuations, and cosmic observations that map how dark energy affects space's expansion. We're entering an era where space's hidden properties are becoming accessible to direct investigation. The question, what is space made of, turns out to be equivalent to asking, what is reality made of? Because space appears to be the fundamental layer of existence from which matter, energy, forces, and possibly consciousness all emerge. We're not just studying cosmic geography, we're investigating the source code of reality itself. What makes this investigation even more profound is that consciousness might be intimately connected to space's structure. Some theories suggest that awareness requires the integration of information across space, making consciousness dependent on space's information processing capabilities. Others propose that consciousness might actually be a fundamental feature of space itself. If you're ready to explore the deepest mystery of existence and discover what the apparent emptiness around you is actually made of, subscribe and hit thumbs up. And here's a question that will transform how you see reality. If space isn't empty, but is actually the most active and fundamental component of existence, what does this tell us about the relationship between mind and cosmos? Comment below with your thoughts on whether consciousness emerges from space or whether space emerges from consciousness. The journey we're about to take will challenge every assumption you have about emptiness, nothingness, and the nature of reality itself. We'll discover that space is not only made of something but might be the most important something in existence, the fabric from which everything else is woven, the field in which all phenomena arise, and possibly the source of consciousness itself. We'll explore quantum foam bubbling at microscopic scales, Einstein's curved spacetime, fabric dark energy's mysterious expansion, drive virtual particles that violate conservation laws, information matrices that might be more fundamental than matter, hidden dimensions that could extend to infinity, and the possibility that space itself might be conscious. By the end of this exploration, you'll understand that the empty space around you is actually the most densely packed, energetically active, informationally rich medium in the universe, and that understanding space's true nature might be the key to understanding everything else, including the mystery of your own existence within this strange, wonderful, and utterly non-empty cosmic medium we call space. The answer to what is space made of will transform not just your understanding of physics, but your understanding of what it means to exist as a conscious being embedded in the most mysterious and fundamental aspect of reality itself. Now let's begin our journey into the heart of space and discover what the universe is truly made of at its deepest level. Chapter 1. Empty Illusion. The first and most crucial realization about space is that emptiness is a complete illusion created by the limitations of human perception and the assumptions of classical physics. What appears to be vacuum void or nothingness is actually the most active and energetic medium in the universe, teeming with quantum activity permeated by fields and structured by geometric properties that make it far more substantial than any material object you've ever encountered. The illusion of empty space arises because human senses evolved to detect matter and energy at scales much larger than the quantum processes that give space its fundamental character. Your eyes see only electromagnetic radiation in narrow wavelength ranges. Your ears detect only mechanical vibrations in matter, and your sense of touch responds only to electromagnetic forces between atoms. None of these senses can directly perceive the quantum fields, virtual particles, and spacetime curvature that make space anything but empty. Ancient Greek philosophers like Democritus proposed that reality consisted of atoms moving through void, indivisible particles of matter separated by regions of absolute nothingness. This atomic theory seemed to require empty space as a container where atoms could move and interact, creating the first systematic theory that space is fundamentally empty except where matter happens to exist. Aristotle rejected the concept of void, arguing that nature abhors a vacuum and that space must be filled with some kind of medium. His plenum theory suggested that space contains invisible substances that transmit forces and fill all apparent emptiness. While Aristotle's specific ideas were wrong, his intuition that space contains hidden reality was remarkably prescient. The scientific revolution of the 16th and 17th centuries revived atomic theories and empty space concepts through the work of scientists like Galileo, Descartes, and Newton. Newton's mechanics required absolute space, a fixed, unchanging reference frame that provided the stage for gravitational interactions and mechanical motion. This absolute space was conceived as geometrically perfect but physically empty. Newton's conception dominated physics for over 200 years and created the modern intuition that space is a passive container rather than an active participant in physical processes. In Newtonian physics, space provides coordinates for describing where things happen, but has no properties of its own beyond geometric relationships. Matter moves through space. Forces act across space, but space itself remains unchanged and unaffected. The first cracks in empty space theory appeared with electromagnetic field theory in the 19th century. James Clerk Maxwell's equations describing electromagnetic phenomena required fields that extend throughout space, carrying energy and momentum even in regions containing no matter. These electromagnetic fields suggested that space has structure and properties beyond pure geometric emptiness. The concept of the luminiferous ether emerged as an attempt to reconcile electromagnetic fields with empty space assumptions. Scientists proposed that space contains an invisible medium called ether that carries electromagnetic waves just as water carries ocean waves or air carries sound waves. The ether was imagined as filling all space while being undetectable by mechanical means. However, the famous Michelson-Morley experiment in 1887 failed to detect Earth's motion through the supposed ether, creating a crisis for electromagnetic theory that was unresolved until Einstein's special relativity eliminated the need for ether by showing that electromagnetic fields are fundamental properties of spacetime itself rather than disturbances in a material medium. Einstein's general relativity dealt the death blow to empty space concepts by revealing that space and time form a dynamic fabric called spacetime that curves in response to matter and energy. In general relativity, space isn't empty. It has geometric properties like curvature that affect how matter moves and how time flows. Spacetime becomes a physical entity with measurable properties rather than abstract nothingness. The curvature of spacetime means that space has structure even in regions containing no matter. Empty space near massive objects is curved differently than empty space far from matter, creating gravitational effects that demonstrate space's non-empty nature. The famous prediction that light bends when passing near massive objects proved that space has properties that affect electromagnetic radiation. Quantum mechanics revealed even more dramatic departures from empty space concepts through the discovery of quantum fields and virtual particles. The Heisenberg uncertainty principle prevents any region of space from being completely empty because uncertainty relations forbid zero energy and zero field values simultaneously. Every point in space must contain minimum amounts of field fluctuations called zero-point energy. Quantum field theory describes space as filled with quantum fields for every fundamental particle and force. These fields extend throughout the universe and carry energy even in their lowest energy states, called vacuum states. The electromagnetic field, electron field, quark fields, neutrino fields, and other quantum fields all contribute energy density to apparently empty space. The Casimir effect provides direct experimental evidence that space contains real energy through quantum field fluctuations. When two uncharged metal plates are placed extremely close together in vacuum, quantum field fluctuations between the plates differ from fluctuations outside the plates, creating measurable attractive forces that bring the plates together. This effect demonstrates that vacuum has physical properties that can be manipulated and measured. Modern calculations of quantum vacuum energy density yield results that are incomprehensibly large, perhaps 10,120 times larger than observed cosmic energy densities. This cosmological constant problem represents the worst theoretical prediction in physics, but it confirms that space contains enormous amounts of energy even when no matter is present. Zero-point energy pervades every cubic centimeter of space, creating quantum fluctuations that affect atomic behavior, molecular chemistry, and electromagnetic phenomena. These vacuum fluctuations contribute to the Lamb shift in hydrogen atom energy levels, spontaneous emission rates for excited atoms, and the magnetic moments of fundamental particles. Quantum chromodynamics reveals that even the protons and neutrons in atomic nuclei emerge from quantum field fluctuations in space rather than being fundamental particles. Quarks and gluons are confined within nucleons by color force fields that fill space throughout the nucleus, making atomic matter itself a manifestation of structured space rather than objects existing in empty space. Dark energy observations have revealed that space contains additional energy components beyond quantum vacuum fluctuations. The accelerating expansion of the universe requires dark energy density approximately 10 to 29 grams per cubic centimeter, vastly smaller than quantum field theory predictions, but still representing a fundamental property of space itself. This dark energy appears to be vacuum energy that drives cosmic expansion while remaining invisible to electromagnetic observations. Unlike matter or radiation that becomes diluted as the universe expands, dark energy density remains constant as space stretches, suggesting that dark energy is created as space itself is created during cosmic expansion. Gravitational wave observations by LIGO and other detectors have provided direct evidence that space has mechanical properties by measuring how gravitational waves stretch and compress space itself. These observations prove that space can be distorted, oscillate, and carry energy and momentum like any physical medium. The detection of gravitational waves from black hole mergers and neutron-star collisions demonstrates that violent, astronomical events create ripples in spacetime that propagate across cosmic distances at light speed. These spacetime distortions are real physical phenomena that affect the geometry of space and the flow of time throughout their propagation. Vacuum birefringence experiments attempt to detect how intense magnetic fields affect quantum vacuum properties by changing the polarization of light passing through strong magnetic regions. These experiments probe whether electromagnetic fields can modify space's optical properties through interactions with virtual particle pairs. Recent theoretical work suggests that space might be constructed from more fundamental entities like quantum entanglement networks, information processing systems, or discrete geometric units that combine to create the appearance of continuous spacetime. In these theories, space emerges from deeper levels of reality rather than being fundamental itself. The holographic principle proposes that three-dimensional space might be constructed from information stored on two-dimensional boundaries, similar to how holograms encode three-dimensional images on flat surfaces. This would mean that space's apparent three-dimensionality is an emergent property of information processing rather than a fundamental geometric fact. Digital physics theories suggest that space might be computational rather than geometric, a discrete information processing system that creates the appearance of continuous spatial extension through rapid computation. In these models, space is made of bits rather than geometric points, with physical laws emerging as algorithms operating on cosmic databases. Understanding that empty space is an illusion transforms our perspective on existence itself. We don't live in a universe where matter occasionally interrupts vast emptiness. We live in a universe where space is the most fundamental and active component, with matter representing temporary organizing patterns in the underlying spatial medium. The recognition that space has structure, energy, and dynamic properties means that consciousness doesn't exist in empty space, but rather emerges from and participates in space's information processing capabilities. The boundary between mind and space becomes blurred when space itself has computational and informational properties that might be essential for consciousness. This revolution in understanding space-day's nature forces us to reconceptualize everything from atomic structure to cosmic evolution to the relationship between consciousness and physical reality. Space isn't the passive stage where existence unfolds. It is the active medium from which existence continuously emerges through processes we're only beginning to understand. Chapter 2. Quantum foam at the smallest possible scales of space and time. The realm governed by quantum mechanics and general relativity simultaneously. Space reveals its most bizarre and fundamental nature as quantum foam, a bubbling, fluctuating medium where the familiar concepts of distance, duration, and geometric smoothness completely break down. This microscopic structure of space represents reality's deepest level, where space itself becomes uncertain, discontinuous, and more like a frothy sea than the smooth fabric our everyday experience suggests. Quantum foam emerges from the inevitable collision between quantum uncertainty principles and Einstein's general relativity when we examine space at the Planck scale. Distances of approximately 10 to 35 meters and times of approximately 10 to 43 seconds. At these scales, quantum uncertainty in energy and momentum becomes so large that space-time geometry itself becomes uncertain, fluctuating wildly between different possible configurations. Dr. John Wheeler, who coined the term quantum foam, described this phenomenon as the breakdown of classical spacetime geometry when quantum effects become comparable to gravitational effects. Wheeler realized that Heisenberg's uncertainty principle prevents spacetime from having definite geometric properties at Planck scales because the energy required to measure position precisely would create gravitational fields so intense they would curve spacetime unpredictably. The mathematics of quantum foam involves combining quantum field theory with general relativity through calculations that push both theories to their absolute limits. When quantum uncertainty in position becomes comparable to the Compton wavelength of virtual particles, the energy density becomes so large that it creates significant spacetime curvature according to Einstein's equations. These calculations reveal that space at Planck scales resembles a violent storm where virtual black holes spontaneously form and evaporate, wormholes open and close, and the topology of space constantly changes through quantum tunneling between different geometric configurations. The smooth spacetime we observe at larger scales emerges as a statistical average over these microscopic fluctuations. Quantum foam affects every point in space throughout the universe, from the vacuum between galaxies to the interior of atomic nuclei. The familiar three-dimensional geometry we experience represents the large-scale averaging of countless quantum geometric fluctuations occurring at scales too small to observe directly with any conceivable technology. Recent theoretical work by Dr. Carlo Rovelli and others in loop quantum gravity suggests that space might be literally made of quantum foam, discrete geometric units called atoms of space that combine and interact to create macroscopic spacetime geometry. In this picture, quantum foam isn't just a disturbance in space. It is space at the fundamental level. These atoms of space, or quantogeometry, have finite size approximately equal to the Planck length and combine through quantum superposition and entanglement to create larger spatial structures. The smooth spacetime of general relativity emerges when enormous numbers of these geometric quanta organize into coherent patterns through quantum processes. Loop quantum gravity calculations suggest that space has granular structures similar to how matter appears continuous at large scales but consists of discrete atoms at microscopic scales. Just as water appears smooth Despite being made of molecules, space appears geometrically smooth despite being made of discrete, geometric units fluctuating through quantum foam dynamics. The implications of granular space structure are profound for understanding cosmic evolution, black hole physics, and the relationship between quantum mechanics and gravity. If space truly has atomic structure, then concepts like infinite density and infinite spacetime curvature, mathematical singularities that plague general relativity, might be eliminated by the finite size of geometric quanta. Quantum foam also affects the propagation of light and matter through space by creating microscopic variations in the speed of light, photon polarization, and particle interaction rates. These effects are extraordinarily small, but might be detectable through precision astronomical observations of distant gamma-ray bursts, cosmic ray interactions, and gravitational wave propagation. Dr. Amelino Camiglia and others have proposed tests of quantum foam effects through observations of high-energy photons from distant astronomical sources. If space has discrete structure at Planck scales, photons of different energies might travel at slightly different speeds over cosmic distances, creating detectable time delays in gamma-ray burst observations. The Fermi Gamma-Ray Space Telescope and other high-energy astronomical observatories have searched for these quantum foam signatures by measuring arrival times of photons with different energies from distant galaxies. So far, no definitive evidence for discrete space structure has been detected, placing constraints on possible quantum foam theories. Virtual particle production in quantum foam creates what physicists call the quantum vacuum, a state that contains no real particles but enormous amounts of virtual particle activity. These virtual particles appear in particle-antiparticle pairs that exist for extremely brief periods, before annihilating each other in accordance with quantum uncertainty principles. The energy associated with virtual particle pairs in quantum foam creates vacuum pressure that affects the expansion rate of space, the stability of atomic matter, and the behavior of electromagnetic fields. Calculations suggest that quantum vacuum energy density approaches 1,094 grams per cubic centimeter, a number so large it would cause immediate gravitational collapse if it coupled to gravity at full strength. The fact that observed cosmic expansion proceeds at measured rates rather than collapsing under quantum vacuum energy suggests either that most vacuum energy doesn't couple to gravity, that unknown physics cancels most vacuum energy effects, or that our calculations of quantum foam energy are fundamentally incorrect. String theory approaches quantum foam through the concept of spacetime uncertainty arising from string vibrations at Planck scales. In string theory, fundamental particles are tiny vibrating loops whose quantum fluctuations create uncertainty in spacetime geometry similar to quantum foam effects, but described through higher dimensional mathematics. The extra dimensions required by string theory might provide space for quantum foam energy to spread out, reducing its effective density in our observed three-dimensional space. String foam might involve vibrations that extend into 6 or 7 additional spatial dimensions, making quantum geometry far more complex than simple three-dimensional foam models suggest. Causal set theory proposes another approach to quantum foam through the idea that spacetime consists of discrete points connected by causal relationships, rather than continuous geometric manifolds. In causal sets, space emerges from networks of discrete events connected by cause and effect relationships, creating foam-like structure at fundamental scales. The holographic principle suggests that quantum foam in three-dimensional space might be encoded as information on two-dimensional boundaries, similar to how three-dimensional holographic images are stored on flat surfaces. This would mean that quantum foam cis-complexity and information content might be limited by the area of surfaces rather than the volume of space. Recent work on entanglement entropy in quantum field theory reveals deep connections between quantum foam and information theory. The entanglement between quantum fields in different regions of space creates correlations that might be responsible for spacetime connectivity and geometric structure at microscopic scales. Dr. Mark van Ramsdonk and others have shown that quantum entanglement between matter fields might actually create spacetime geometry through emergent geometric relationships. In this picture, quantum foam represents the underlying entanglement network from which classical spacetime emerges as a large-scale, approximate description. Black hole physics provides another window into quantum foam structure through Hawking radiation calculations that depend on virtual particle pairs near event horizons. The production of Hawking radiation involves quantum foam fluctuations, where virtual particles become real through black hole gravitational effects. The information paradox in black hole evaporation might be resolved through understanding how quantum foam preserves and processes information during gravitational collapse and subsequent evaporation. Recent firewall and fuzzball proposals suggest that black hole event horizons might be thick layers of quantum foam rather than geometric surfaces. Quantum foam experiments represent one of the frontiers in fundamental physics, attempting to detect the discrete structure of space through precision measurements of light propagation, atomic behavior, and gravitational effects. These experiments must achieve sensitivity to effects occurring at scales 1,020 times smaller than atomic nuclei. Atomic interferometry experiments attempt to measure quantum foam effects through precision measurements of atomic wave function evolution in carefully controlled gravitational fields. If space has discrete structure, atomic matter waves might interact with geometric quanta in ways that create detectable phase shifts. Gravitational wave detectors like LIGO might eventually achieve sensitivity sufficient to detect quantum foam effects through measurements of spacetime metric fluctuations at Planck scales. Future generations of gravitational wave observatories might observe the quantum mechanical behavior of spacetime geometry itself. The study of quantum foam forces us to confront fundamental questions about the relationship between mathematics and physical reality. If space is made of discrete geometric units undergoing quantum fluctuations, then the mathematical concepts of continuity, smoothness, and infinite divisibility might not apply to physical space at the deepest level. Understanding quantum foam might be essential for developing theories of quantum gravity that unify general relativity and quantum mechanics into a single theoretical framework. The foam structure of space might hold the key to resolving the mathematical inconsistencies that arise when quantum effects and gravitational effects operate at comparable scales. Quantum foam also raises profound questions about the relationship between space and consciousness. If consciousness involves information processing that depends on spatial relationships, then the discrete fluctuating nature of space at microscopic scales might place fundamental limits on conscious experience, or might require consciousness to emerge from quantum foam information processing. The recognition that space has quantum foam structure at its deepest level transforms our understanding of existence from objects moving through empty space to patterns of organization emerging from the quantum information processing that creates space itself. We do and live on quantum foam. We are temporary stable patterns in the cosmic quantum foam that fills all of reality. Chapter 3. Fabric Reality. Einstein's general relativity revealed that space is not the empty container of Newtonian physics, but rather a dynamic fabric called spacetime that bends, stretches, and curves in response to matter and energy. This spacetime fabric is so real and substantial that it can ripple with gravitational waves, store enormous amounts of energy, and determine how matter moves and how time flows throughout the universe. Understanding spacetime as fabric transforms our conception of space from void to medium, from background to protagonist in cosmic evolution. The fabric metaphor captures essential aspects of spacetime's behavior while remaining accessible to intuitive understanding. Like a stretched rubber sheet that deforms when masses are placed upon it, space-time curves in response to matter and energy according to Einstein's field equations. Objects do not fall toward massive bodies because of mysterious forces acting across empty space. They follow the straightest possible paths through curved space-time geometry. Dr. John Wheeler summarized this revolutionary insight in his famous phrase, "Space-time tells matter how to move. Matter tells space-time how to curve." This reciprocal relationship between geometry and matter eliminates the need for gravitational forces by replacing them with geometric properties of space-time itself. Gravity becomes geometry rather than force, curvature rather than attraction. The mathematical description of space-time fabric involves tensor calculus and differential geometry that extend far beyond everyday mathematical experience. Einstein's field equations relate space-time curvature to energy density through mathematical relationships so elegant that they suggest deep underlying principles governing cosmic organization and evolution. These equations predict that space-time has mechanical properties similar to elastic materials. It can be stretched, compressed, twisted, and set into oscillations that propagate as gravitational waves. The recent detection of gravitational waves by LIGO and other observatories provides direct evidence that space-time behaves like a physical medium with measurable mechanical properties. Gravitational wave observations reveal that space-time fabric can store and transport enormous amounts of energy across cosmic distances. When two black holes spiral together and merge, they convert substantial fractions of their rest mass into gravitational wave energy that propagates through space-time at exactly the speed of light. The energy carried by gravitational waves represents pure space-time energy, energy stored in the geometric curvature of space itself rather than in matter or electromagnetic fields. This demonstrates that space-time fabric is not just geometrically active, but energetically substantial, capable of carrying energy densities comparable to electromagnetic radiation. Space-time curvature affects not only the motion of matter, but also the flow of time itself through gravitational time dilation effects. Time passes more slowly in regions of stronger gravitational fields, meaning that space-time fabric doesn't just curve space, but also curves time in ways that fundamentally alter the relationship between temporal and spatial dimensions. GPS satellites must account for gravitational time dilation effects to maintain accurate positioning because their clocks run faster in the weaker gravitational field at orbital altitudes compared to clocks on Earth's surface. These technological applications demonstrate that space-time curvature has measurable effects on information processing and technological systems. The extreme curvature near black holes creates regions where space-time geometry becomes so distorted that space and time dimensions exchange roles. Inside black hole event horizons, the radial spatial dimension becomes time-like, while the time dimension becomes space-like, creating geometric conditions unlike anything in ordinary experience. Near rotating black holes, space-time fabric gets dragged around by the black hole's rotation in a phenomenon called frame dragging, or the lens-thirring effect. This space-time dragging means that even light beams and gyroscopes get carried along with the rotation of space-time itself, demonstrating that space-time has properties analogous to viscous fluids. Recent observations of frame dragging effects around Earth using satellite gyroscope experiments confirm that even our planet's relatively weak gravitational field and slow rotation create measurable distortions in local space-time fabric. These measurements prove that space-time curvature is not limited to exotic astronomical objects, but occurs throughout the cosmos. Cosmic expansion represents another manifestation of space-time fabric as dynamic nature through the stretching of space itself rather than motion of galaxies through static space. The Hubble law relating galaxy recession velocity to distance results from space expansion that carries galaxies apart while they remain nearly stationary relative to local space-time coordinates. Dark energy affects spacetime fabric by causing accelerating cosmic expansion that appears to stretch space at increasing rates. This expansion energy seems to be a property of spacetime itself rather than energy moving through space, suggesting that spacetime fabric has intrinsic energy densities that drive cosmic evolution. The relationship between quantum mechanics and spacetime fabric remains one of physics' greatest unsolved problems, because quantum field theory treats space and time as fixed backgrounds, while general relativity treats spacetime as dynamical. Reconciling these approaches requires understanding how quantum effects modify spacetime geometry and how spacetime curvature affects quantum field behavior. Quantum field theory in curved spacetime reveals that spacetime curvature affects virtual particle production, vacuum energy density, and particle creation rates near black holes and during cosmic expansion. The Hawking radiation process involves quantum field interactions with curved spacetime that convert virtual particles into real particles at black hole event horizons. The Unruh effect demonstrates that spacetime curvature and acceleration create temperature-like properties in quantum vacuum that cause accelerated observers to detect thermal radiation in apparently empty space. This effect reveals deep connections between spacetime geometry, quantum fields, and thermodynamic properties that suggest spacetime might have temperature and entropy. Thermodynamic properties of spacetime fabric become apparent in black hole physics, where event horizon area corresponds to black hole entropy, according to the Bekenstein-Hawking formula. This relationship suggests that spacetime geometry encodes information, and that black holes are thermodynamic systems with temperature, entropy, and heat capacity. The holographic principle emerges from black hole thermodynamics and suggests that spacetime fabric in any region can be completely described by information encoded on the boundary of that region. This would mean that three-dimensional spacetime is constructed from two-dimensional information in ways analogous to holographic image reconstruction. If spacetime is indeed holographic, then the fabric metaphor takes on new meaning, where the three-dimensional fabric we experience emerges from information processing on distant two-dimensional surfaces. Spacetime curvature would represent information processing patterns rather than geometric deformation of physical material. String theory describes spacetime fabric as emerging from the collective behavior of fundamental strings vibrating in higher dimensional space. In this picture, the familiar four dimensions of spacetime represent a subset of a larger geometric structure where string vibrations create the appearance of curved four-dimensional spacetime fabric. Extra dimensions in string theory might mean that spacetime fabric extends far beyond the four dimensions we can observe directly. Spacetime curvature in these hidden dimensions could affect observable physics through modifications to gravitational strength, particle masses, and force coupling constants. Loop quantum gravity approaches spacetime fabric through the concept of discrete geometric building blocks that combine to create macroscopic spacetime curvature. Rather than being infinitely divisible, spacetime fabric might consist of finite-sized geometric units that interact through quantum mechanical principles. The geometric units of loop quantum gravity have finite area and volume, eliminating the mathematical singularities that plague general relativity while preserving Einstein's insights about spacetime curvature. Spacetime fabric becomes granular rather than continuous, similar to how matter appears smooth despite being made of discrete atoms. Causal set theory proposes that spacetime fabric emerges from networks of discrete events connected by causal relationships. In this approach, spacetime geometry arises from the combinatorial structure of cause and effect relationships rather than from continuous geometric manifolds. Emergent gravity theory suggests that spacetime fabric itself might be an emergent property of deeper microscopic physics, rather than being fundamental. Just as thermodynamics emerges from statistical mechanics, despite Temperature and pressure being absent from individual molecular dynamics, spacetime curvature might emerge from underlying processes that don't involve geometry directly. The idea that spacetime fabric might be emergent rather than fundamental raises profound questions about the relationship between space, time, matter, and consciousness. If spacetime emerges from information processing or quantum entanglement networks, then consciousness might be intimately connected to the processes that create spacetime fabric. Some theories propose that consciousness involves information integration across spatial regions in ways that depend on spacetime connectivity and causal structure. The geometric properties of spacetime fabric might be essential for consciousness emergence through their effects on information flow and integration. Understanding spacetime as fabric reveals that we don't live in space and time, but rather as temporary patterns in spacetime fabric itself. Our bodies, our thoughts, and our experiences represent organizational structures in the cosmic fabric that connects all events throughout the universe as history. The recognition that spacetime has fabric-like properties transforms questions about the nature of existence into questions about geometric dynamics and information processing in curved spacetime. We become geometric phenomena rather than material objects, patterns of spacetime curvature rather than separate entities moving through empty space. This geometric view of existence suggests that consciousness might be a property of spacetime fabric, organization rather than a property of matter arranged in space. Understanding consciousness might require understanding how information processing emerges from the geometric dynamics of curved spacetime rather than from electromagnetic and chemical processes in biological brains. Spacetime fabric represents the stage, the script, and the actors in cosmic drama simultaneously, the medium in which events occur, the laws that govern how events unfold, and the substance from which events are constructed. Recognizing space as fabric rather than void transforms our understanding of existence from mechanical to geometrical, from material to informational, from separate to interconnected, through the cosmic fabric that constitutes the foundation of all reality. Chapter 4. Dark Foundation. Perhaps the most mysterious component filling space is dark energy, a cosmic force that comprises 68% of the universe as total content and appears to be woven into the very fabric of space itself. Unlike matter and radiation that become diluted as the universe expands, dark energy density remains constant as space stretches, suggesting that dark energy is created as space itself is created. This means that space isn't just permeated by dark energy. Space might be dark energy in its fundamental essence. The discovery of dark energy through observations of distant supernova by Dr. Saul Perlmutter and Adam Rees revolutionized cosmology by revealing that cosmic expansion is accelerating rather than decelerating as expected from matter as gravitational attraction. This acceleration requires a form of energy with negative pressure that pushes space apart rather than pulling matter together. Dark energy's negative pressure creates repulsive gravitational effects that overcome matter's attractive gravity on cosmic scales, driving faster and faster expansion of space throughout the universe. This cosmic acceleration affects every cubic centimeter of space from intergalactic voids to the interior of galaxies, though its effects become noticeable only on scales larger than galaxy clusters. The simplest interpretation of dark energy identifies it with Einstein's cosmological constant, a term in general relativity equations that represents vacuum energy density. If empty space has inherent energy density that remains constant as space expands, then cosmic expansion would naturally accelerate as dark energy as relative importance increases compared to matter and radiation that become diluted over time. Quantum field theory predicts that vacuum should indeed have energy density from zero-point fluctuations of quantum fields, but the calculated vacuum energy exceeds observed dark energy density by factors of 10120, the worst theoretical prediction in physics. This cosmological constant problem suggests that either our understanding of vacuum energy is fundamentally incorrect or unknown physics cancels most quantum vacuum energy. Alternative dark energy models propose that cosmic acceleration might be driven by dynamic scalar fields called quintessence that vary over space and time rather than remaining constant like vacuum energy. Quintessence fields could have energy densities and pressures that change during cosmic evolution, potentially explaining why dark energy dominance began only 6.8 billion years ago. Dr. Sean Carroll's theoretical work on dark energy explores whether cosmic acceleration might result from modifications to general relativity itself at cosmic scales rather than from energy sources. These modified gravity theories attempt to explain accelerating expansion through geometric effects rather than mysterious energy components filling space. The phantom dark energy scenario proposes that dark energy density might actually increase over time, leading to runaway cosmic acceleration that eventually overcomes all other forces and tears apart galaxies, stars, atoms, and spacetime itself. Dr. Robert Caldwell's calculations suggest that phantom energy could end the universe in finite time through a Big Rip catastrophe. Observational constraints on dark energy properties come from multiple independent sources, including supernova distance measurements, cosmic microwave background fluctuation patterns, and large-scale galaxy clustering statistics. These observations consistently indicate that dark energy has equation of state parameter very close to -1, matching expectations for vacuum energy. The Planck satellite mission has precise measurements of cosmic microwave background fluctuations, provide the most stringent constraints on dark energy density and equation of state through analysis of how dark energy affects cosmic geometry and the angular size of fluctuation patterns on the cosmic microwave background. Baryon acoustic oscillation surveys measure the characteristic scale of sound waves in the early universe through galaxy clustering patterns, providing geometric tests of cosmic expansion history that are sensitive to dark energy properties. These surveys confirm accelerating expansion while constraining possible time evolution of dark energy density. Dark energy affects not only cosmic expansion, but also the growth rate of cosmic structure through its influence on gravitational collapse rates. Regions of space dominated by dark energy resist gravitational collapse, slowing the formation of galaxy clusters and modifying the cosmic web's evolution over time. The transition from matter-dominated to dark energy-dominated cosmic expansion occurred approximately 6.8 billion years ago when dark energy's repulsive effects began overwhelming matter's gravitational attraction. This transition fundamentally changed cosmic evolution from an era of increasing structure formation to an era of decreasing gravitational interaction rates. Future cosmic evolution under dark energy dominance will see progressive isolation of galaxy groups as cosmic expansion carries them beyond each other as gravitational influence. The local group containing our galaxy will eventually become isolated from all other galaxies as they disappear beyond cosmic horizons created by accelerating expansion. Dark energy's effects on spacetime curvature create cosmic horizons, surfaces beyond which objects recede at light speed due to space expansion, making them forever inaccessible to observation or interaction. These horizons shrink over time as dark energy acceleration carries more and more cosmic territory beyond accessible limits. The holographic principle applied to dark energy suggests that cosmic acceleration might be limited by information processing constraints related to cosmic horizon areas. If the universe operates as a vast information processing system, then dark energy properties might be determined by computational limits rather than fundamental physics. Dark energy interactions with matter remain mysterious because dark energy appears to affect only gravitational phenomena while remaining invisible to electromagnetic, weak nuclear, and strong nuclear forces. This invisibility suggests that dark energy might represent a completely new type of field or energy that interacts only through gravitational coupling. Laboratory searches for dark energy effects attempt to detect fifth forces, modifications to gravitational strength, or vacuum energy variations that might reveal dark energy's microscopic properties. These experiments must achieve extraordinary sensitivity because dark energy effects are negligible at laboratory scales compared to cosmic scales. Chameleon field theories propose that dark energy might have variable strength depending on local matter density, appearing strong in cosmic voids but weak in dense regions like solar systems or laboratory environments. These theories could explain why dark energy affects cosmic expansion without creating detectable effects in laboratory experiments. The coincidence problem in dark energy cosmology asks why dark energy density is comparable to matter density at the current cosmic epoch rather than being vastly larger or smaller. This remarkable coincidence suggests either extraordinary fine-tuning or deeper physical principles that relate dark energy to matter density. Anthropic explanations for dark energy properties propose that conscious observers can only exist during cosmic epochs when dark energy density permits structure formation and stellar evolution. In this view, we observe current dark energy density because consciousness can only emerge when dark energy and matter density are appropriately balanced. Multiverse theories suggest that our universe might be one member of a vast ensemble with different dark energy densities, with observers existing only in universes where dark energy permits complexity and consciousness development. This anthropic selection could explain dark energy's observed properties without requiring fundamental physics principles. The relationship between dark energy and quantum vacuum fluctuations remains one of cosmology's deepest mysteries because quantum field theory predicts vacuum energy densities incompatible with observed cosmic acceleration. Resolving this discrepancy might require new physics that modifies quantum field theory or general relativity at cosmic scales. Supersymmetry theories attempt to resolve the cosmological constant problem by proposing that boson and fermion contributions to vacuum energy cancel exactly in the symmetric phase, leaving only small symmetry-breaking contributions that might match observed dark energy density. Extra-dimensional theories suggest that dark energy in our three-dimensional space might represent leakage from higher-dimensional vacuum energy or gravitational effects from other three-dimensional spaces embedded in higher dimensions. These theories could naturally explain why dark energy density is much smaller than quantum field theory predictions. The landscape of string theory contains approximately 1/500 possible vacuum states with different cosmological constants, potentially providing a statistical explanation for observed dark energy density through anthropic selection among vacuum states that permit observer existence. Dark energy's role as the foundation filling space means that understanding cosmic acceleration requires understanding space as fundamental nature and energy content. Dark energy might not be separate from space, but rather represents space as intrinsic tendency toward expansion and geometric evolution. If dark energy truly is a fundamental property of space itself, then every cubic centimeter of apparently empty space contains dark energy density approximately 6 × 1027 kilograms per cubic meter. This energy density, while extremely small by laboratory standards, dominates cosmic evolution and determines the universe's ultimate fate. The recognition that space is filled with dark energy foundation transforms our understanding of emptiness and void. What appears to be empty space actually contains the dominant component of cosmic reality, an energy field that drives cosmic expansion and shapes cosmic evolution on the largest possible scales. Understanding dark energy as space as foundation reveals that space is not passive container, but active participant in cosmic evolution, continuously creating expansion energy that carries galaxies apart and determines cosmic destiny. We live not in empty space, but in an ocean of dark energy that connects every point in the universe through its expansion effects and gravitational influence. The dark foundation filling space represents one of the universe's greatest mysteries and might hold keys to understanding space as ultimate nature, the relationship between quantum mechanics and gravity, and the cosmic context that makes consciousness possible during this remarkable epoch when dark energy dominance is beginning to shape cosmic destiny. Chapter 5. Virtual Universe. The quantum vacuum filling every cubic centimeter of space is alive with virtual particles, ephemeral matter and antimatter pairs that pop into existence and annihilate faster than light can cross an atomic nucleus. These virtual particles represent one of quantum mechanics' most bizarre predictions and have been experimentally verified through measurable effects on atomic behavior, electromagnetic phenomena, and the mechanical forces between objects in apparent vacuum. Understanding virtual particles reveals that space is not empty void, but a seething ocean of potential existence where the boundary between real and unreal constantly fluctuates. Virtual particles emerge from Heisenberg's uncertainty principle, which states that energy and time cannot be simultaneously measured with perfect precision. This fundamental limitation of quantum mechanics allows particle-antiparticle pairs to borrow energy from vacuum and exist briefly before paying the energy debt by annihilating each other and returning to vacuum state. The lifetime of virtual particle pairs is inversely proportional to their mass energy, according to the time-energy uncertainty relation delta E as delta T is greater than or equal to A2. Massive virtual particles like proton-antiproton pairs exist for approximately 10 to 24 seconds, while lighter virtual electron-positron pairs can exist for up to 10 to 21 seconds before vacuum energy loans must be repaid through annihilation. Dr. Steven Weinberg's calculations show that virtual particle production rates in quantum vacuum are enormous. Approximately 1,048 virtual particle pairs per cubic centimeter per second for all particle types combined. This means that every point in space experiences constant creation and destruction of virtual matter at rates that dwarf any material process occurring in ordinary matter. The Casimir effect provides direct experimental evidence for virtual particle reality through measurements of attractive forces between uncharged metal plates in vacuum. When plates are separated by distances comparable to virtual particle wavelengths, virtual particle fluctuations between plates differ from fluctuations in surrounding vacuum, creating pressure differences that produce measurable mechanical forces. Dr. Marcus Sparnay's precision measurements of Casimir forces confirmed quantum field theory predictions to within experimental accuracy, proving that virtual particles have real physical effects despite their ephemeral existence. Modern Casimir effect experiments achieve force measurement precision approaching femtons, enabling detailed tests of quantum vacuum predictions. The electromagnetic properties of virtual particles affect light propagation through vacuum by creating tiny modifications to photon behavior that accumulate over cosmic distances. Virtual electron-positron pairs interact weakly with real photons through quantum loop corrections that modify electromagnetic interactions in precise ways predicted by quantum electrodynamics. These virtual particle interactions contribute to the running of electromagnetic coupling strength with energy scale, causing the fine structure constant to vary slightly at high energies. Dr. Richard Feynman's quantum electrodynamics calculations incorporating virtual particle corrections achieve agreement with experimental measurements to more than 10 decimal places. Virtual particles also contribute to the magnetic moments of electrons, muons, and other fundamental particles through quantum loop corrections that involve virtual photon and virtual particle interactions. The electromagnetic moment calculated including virtual particle effects agrees with experimental measurements to unprecedented precision, representing one of physics' most successful theoretical predictions. The vacuum birefringence phenomenon occurs when intense magnetic fields interact with virtual particle pairs to create directional dependence in vacuum optical properties. Virtual electron-positron pairs become polarized in strong magnetic fields, causing vacuum to behave like a weak birefringent crystal that affects light polarization differently in different directions. Astronomical searches for vacuum birefringence effects near magnetars neutron stars with magnetic fields exceeding 1015 Gauss attempt to detect polarization changes in light passing through magnetized vacuum. These observations could provide tests of quantum electrodynamics under field conditions impossible to achieve in terrestrial laboratories. The quantum chromodynamics vacuum contains virtual quark-antiquark pairs and virtual gluons that give rise to the mass of protons and neutrons through confinement mechanisms that trap quarks within nucleons. Most of a proton's mass arises from virtual particle interactions rather than from the masses of constituent quarks. Virtual particle interactions in quantum chromodynamics vacuum create instantons, topological fluctuations that contribute to strong force phenomena like theta vacuum effects and possible axion particle production. These vacuum structures might play roles in explaining the matter-antimatter asymmetry observed in cosmic evolution. Hawking radiation near black holes involves virtual particle pairs where one member falls into the black hole while the other escapes as real radiation. This process converts black hole mass energy into thermal radiation through virtual particle interactions with curved spacetime near event horizons. The Unruh effect demonstrates that virtual particles appear different to observers in different acceleration states, with accelerated observers detecting thermal radiation in vacuum that appears empty to inertial observers. This effect reveals deep connections between virtual particles, acceleration, and temperature that suggests spacetime and thermodynamics are intimately related. Virtual particle interactions affect atomic energy levels through vacuum polarization effects that modify electromagnetic interactions between electrons and nuclei. The Lamb shift in hydrogen atom energy levels results from virtual photon interactions that change electron binding energies by amounts, measurable through precision spectroscopy. Spontaneous emission rates for excited atoms depend on virtual photon fluctuations in surrounding vacuum through processes where excited electrons interact with virtual electromagnetic fields to produce real photons and transition to lower energy states. These quantum electrodynamics effects determine atomic lifetimes and spectral line properties. Van der Waals forces between neutral atoms arise from virtual photon interactions that create correlated electronic motion in neighboring atoms. These quantum mechanical forces operate at distances much larger than atomic sizes and play crucial roles in molecular bonding, surface phenomena, and biological processes. The zero-point energy of quantum vacuum represents the minimum possible energy state that remains when all real particles are removed from a region of space. This irreducible energy density arises from virtual particle fluctuations that cannot be eliminated even at absolute zero temperature due to quantum uncertainty principles. Calculations of total vacuum zero-point energy yield infinite results that require mathematical techniques, called renormalization, to extract finite predictions for observable phenomena. The infinities in virtual particle calculations reveal fundamental limitations in current quantum field theory that might require new physics for complete understanding. The cosmological constant problem emerges from attempts to calculate how virtual particle zero-point energy affects cosmic expansion through gravitational interactions. Naive calculations yield vacuum energy densities that would cause immediate gravitational collapse of the universe, conflicting dramatically with observed cosmic acceleration. Dynamic Casimir effect experiments attempt to create real photons from virtual particles through rapid modulation of boundary conditions in quantum vacuum. Dr. Christopher Wilson's experiments using superconducting circuits have successfully observed photon production from virtual photons through resonator frequency modulation at gigahertz rates. Squeezed vacuum states represent quantum mechanical modifications of virtual particle statistics that reduce quantum noise in some observables, while increasing noise in complementary variables according to uncertainty principle requirements. These engineered vacuum states enable precision measurements beyond standard quantum limits in gravitational wave detectors and atomic clocks. Virtual particle interactions in curved spacetime near black holes create information processing challenges that contribute to black hole information paradox discussions. Whether information carried by virtual particles can escape black holes through Hawking radiation remains controversial among theoretical physicists studying black hole thermodynamics. The holographic principle applied to virtual particles suggests that virtual particle information in any spatial volume might be encoded on boundary surfaces rather than being distributed throughout three-dimensional vacuum. This could resolve infinities in virtual particle calculations by limiting information density to boundary areas. String theory describes virtual particles as vibrating loops in higher dimensional space, with virtual particle properties determined by string vibration modes and extra-dimensional geometry. Virtual particle interactions might provide windows into extra-dimensional physics through precision measurements of quantum loop corrections. Consciousness and virtual particles might be connected through quantum mechanical processes in biological systems that depend on virtual particle interactions. Some theories propose that consciousness involves quantum coherence effects that could be sensitive to virtual particle fluctuations in neural microtubules or synaptic processes. The recognition that space is filled with virtual particles transforms our understanding of vacuum from empty nothingness to dynamic medium where potential existence constantly fluctuates on the edge of reality. Virtual particles represent the universe's creativity at its most fundamental level, where quantum uncertainty enables continuous exploration of possible existences. Understanding virtual particles reveals that the boundary between existence and non-existence is far more fluid than classical physics suggested. Virtual particles exist in liminal states between real and unreal, demonstrating that reality operates through processes that transcend simple binary categories of existence and void. The virtual universe filling space suggests that consciousness might emerge from similar liminal processes where potential mental states fluctuate on the edge of awareness before occasionally becoming conscious thoughts and experiences. The quantum vacuum's creativity might be reflected in consciousness' ability to generate novel ideas and experiences from apparent emptiness. Virtual particles represent space as fundamental creative capacity, the ability to generate existence from nothingness through quantum mechanical processes that operate at every point throughout the universe. We live not in empty space, but in an ocean of virtual creativity where potential existence continuously explores possible forms before returning to quantum vacuum potential. Chapter 6. Information Matrix. Recent theoretical breakthroughs in physics suggest that space might not be made of particles, fields, or geometric fabric, but rather of pure information, mathematical information that creates the appearance of three-dimensional spatial extension through computational processes operating on cosmic databases. This informational view of space, emerging from quantum gravity research, black hole thermodynamics, and the holographic principle, suggests that asking what space is made of is like asking what a computer program is made of. The answer involves information processing rather than physical substances. The information theory of space began with Dr. Jacob Bekenstein's discovery that black holes have entropy proportional to their event horizon surface area rather than their volume. Since entropy measures information content, this relationship suggests that all information about matter inside a black hole is encoded on its two-dimensional boundary rather than being distributed throughout its three-dimensional interior volume. Stephen Hawking's black hole thermodynamics. Research revealed that black holes behave like thermodynamic systems with temperature, entropy, and heat capacity determined by their geometric properties. The Hawking temperature of black holes, inversely proportional to their mass, suggests that black holes process information through quantum mechanical mechanisms that relate geometric properties to information content. The holographic principle, developed by Dr. Gerard 't Hooft and Leonard Susskind, generalizes black hole information storage to suggest that any volume of space can be completely described by information stored on its boundary surface. This principle implies that three-dimensional space might be constructed from two-dimensional information processing, similar to how holograms encode three-dimensional images on flat surfaces. Dr. Juan Maldacena, SADC-CFT correspondence, provides the most precise mathematical realization of holographic information processing by showing that gravitational theories in curved spacetime are exactly equivalent to non-gravitational quantum field theories operating on boundary surfaces. This duality demonstrates that spacetime geometry emerges from boundary information processing. The DSCFT correspondence reveals that Einstein's general relativity in certain curved spacetimes is mathematically identical to quantum field theories without gravity, operating on the boundaries of those spacetimes. This relationship suggests that spacetime curvature, gravitational interactions, and three-dimensional spatial extension all emerge from information processing on lower-dimensional boundaries. Quantum error correction provides another connection between information theory and space through discoveries that quantum error correcting codes share mathematical structures with spacetime geometries in holographic theories. Dr. Daniel Gottsman's quantum coding theory appears naturally in holographic spacetime construction, suggesting deep connections between information preservation and spatial geometry. The emergence of spacetime from quantum entanglement represents one of the most startling developments in theoretical physics. Dr. Mark van Ramsdonk and others have shown that quantum entanglement between different regions of boundary quantum fields creates spatial connectivity in the emergent three-dimensional spacetime through geometric relationships that depend on entanglement entropy. When quantum entanglement between boundary regions is strong, the corresponding spatial regions in emergent spacetime are connected by short geodesic paths. When entanglement is weak or absent, spatial regions become disconnected or separated by large distances. Spacetime connectivity emerges from quantum information correlations rather than being fundamental to geometric structure. This entanglement geometry relationship suggests that space might be constructed from networks of quantum entanglement that create spatial relationships through information correlation patterns. Distance, adjacency, and geometric connectivity emerge from the strength and structure of quantum entanglements between information processing elements. Digital physics theories, developed by researchers like Dr. Edward Fredkin and Stephen Wolfram, propose that spacetime operates as a discrete computational system where physical laws emerge as algorithms operating on cosmic databases. In these theories, space consists of discrete information processing units that create the appearance of continuous spatial extension through rapid computation. Cellular automaton models of spacetime suggest that space might consist of simple computational elements that follow local rules to create complex global behaviors, including particle interactions, field dynamics, and geometric relationships. Dr. Konrad Zus's early proposals for digital physics envisioned reality as computational rather than mechanical or geometric. The it from bit hypothesis, proposed by Dr. John Wheeler, suggests that physical reality emerges from binary information processing rather than information emerging from physical processes. In Wheeler's view, Asking fundamental questions about physical systems yields binary answers that constitute the information from which physical properties emerge. Quantum computation theory reveals that information processing can simulate physical systems with exponential efficiency advantages over classical computation, suggesting that physical systems might actually be information processing systems rather than mechanical systems that can be simulated by computation. Quantum computers don't just model physics, they might reveal physics' computational nature. Dr. Seth Lloyd's calculations of cosmic information processing capacity show that the universe can perform approximately 10,120 elementary operations on 1,090 bits of information since the Big Bang. These numbers represent the maximum possible computation that could occur within cosmic volume and time constraints imposed by the speed of light and quantum mechanics. If space is indeed constructed from information processing, then these cosmic computational limits place constraints on spatial structure, particle interactions, and physical law complexity. The finite information processing capacity of cosmic spacetime might determine how complex physical systems can become and how much information they can store and process. The black hole information paradox takes on new significance in informational theories of space because it becomes a question about information preservation during computational processes rather than physical processes. Whether information is preserved when matter crosses black hole event horizons becomes a question about cosmic database integrity during extreme computational conditions. Recent proposals for resolving the information paradox suggest that black hole interiors might be computational constructions that exist only when observed from outside the black hole. The interior spacetime gets computed dynamically based on boundary information processing rather than existing as persistent three-dimensional geometry. Quantum mechanics in informational spacetime theories becomes a description of how cosmic information processing systems maintain coherence and process quantum correlations across space and time. Wave functions describe information states rather than physical configurations, and quantum measurement involves information extraction from cosmic databases. The measurement problem in quantum mechanics might be resolved through understanding how information processing systems extract definite classical information from quantum superposition states. Decoherence occurs when cosmic information processing systems lose quantum correlation information through environmental interactions. Consciousness in informational theories of space becomes a type of information integration process that emerges when cosmic information processing achieves sufficient complexity and self-reference. Dr. Giulio Tomoni's integrated information theory provides mathematical frameworks for understanding how consciousness emerges from information integration across spatial networks. If space is constructed from information processing, then consciousness might involve accessing and integrating cosmic information processing capabilities in ways that create subjective experience and awareness. The boundary between mind and space becomes blurred when space itself has computational and informational properties. String theory's relationship to informational space theories involves understanding how string vibrations in higher dimensional space might represent information processing algorithms operating on cosmic databases. String dynamics could be computational processes rather than physical motions through geometric space. Loop. Quantum gravity approaches informational space through discrete geometric elements that might represent information processing units rather than geometric building blocks. The quantized areas and volumes in loop quantum gravity could be measures of information storage and processing capacity rather than fundamental geometric properties. Causal set theories describe spacetime as networks of discrete events connected by causal relationships, which naturally lends itself to informational interpretations where events represent information. Processing operations and causal connections represent information flow pathways through cosmic computational networks. The fine-tuning of physical constants might reflect optimization of cosmic information processing efficiency, rather than random parameter values or anthropic selection effects. Physical laws might be computational algorithms optimized for maximum information integration and processing capacity within cosmic resource constraints. Laboratory tests of informational space theories involve searching for discrete structure in spacetime through precision. Measurements of light propagation, atomic behavior, and gravitational effects. If space has discrete computational structure, these effects might be detectable through experiments that probe space's information processing properties. Quantum information experiments using trapped ions, superconducting circuits, and photonic systems might provide analogies or direct tests of how cosmic information processing creates spatial relationships and physical phenomena. Quantum computers might be investigating space's computational nature through their own information processing capabilities. The philosophical implications of informational space theories challenge traditional distinctions between mind and matter, software and hardware, real and virtual. If space is pure information processing, then all physical phenomena become informational phenomena, and consciousness becomes a natural feature of sufficiently complex information integration systems. Understanding space as information matrix transforms questions about existence from what is matter made of to what information processes create the appearance of material existence. We become information integration patterns rather than material objects, temporary organizations of cosmic information processing rather than separate entities existing in space. The recognition that space might be made of information rather than substance revolutionizes our understanding of physical reality and suggests that consciousness and cosmos are intimately related through information processing principles that operate at scales from quantum mechanics to cosmic evolution. Space becomes not the container of existence, but the information processing system that continuously creates existence through computational processes we are only beginning to understand. This informational view of space suggests that reality is far more creative, dynamic, and consciousness-like than material physics suggested, opening possibilities for understanding consciousness, free will, and meaning in ways that recognize mind and cosmos as different aspects of cosmic information processing systems that create the appearance of spatial existence through pure computational creativity. Chapter 7. Dimensional Secrets. Beyond our familiar three dimensions of space lies one of the most profound secrets about space as true nature. The possibility that spatial reality extends into additional dimensions that remain hidden from ordinary observation, but may be essential for understanding what space is actually made of. These extra dimensions, required by string theory and other advanced physics theories, suggest that our three-dimensional experience represents only a tiny subset of space's full-dimensional structure, with most of spatial reality existing beyond our perceptual and technological reach. The concept of extra spatial dimensions emerged from early attempts to unify electromagnetic and gravitational forces through geometric theories. In the 1920s, Theodor Kaluza and Oscar Klein proposed that adding a fifth dimension to Einstein's four-dimensional spacetime could naturally incorporate electromagnetic fields as geometric properties of higher dimensional space, suggesting that forces emerge from dimensional structure we cannot directly perceive. Modern string theory requires 6 or 7 additional spatial dimensions beyond our familiar 3 for mathematical consistency, predicting a total of 9 or 10 spatial dimensions plus time. Dr. Michael Green and John Schwartz's superstring theory showed that fundamental particles are actually tiny vibrating loops in this higher dimensional space, with particle properties determined by vibration patterns in the extra dimensions. The extra dimensions in string theory must be compactified, curled up into extremely small sizes, to explain why we observe only 3 large spatial dimensions in everyday experience. Dr. Edward Witten's calculations suggest that extra dimensions have sizes comparable to the Planck. Length, 1035 meters, making them far too small to detect through ordinary physical experiments. The geometry of compactified extra dimensions determines fundamental physics properties like particle masses, force strengths, and coupling constants through the way string vibrations propagate in higher dimensional space. Different compactification geometries yield different low-energy physics, potentially explaining why physical constants have their observed values. Calabi-Yau manifolds represent the most studied mathematical structures for extra-dimensional compactification, providing 6-dimensional geometries that preserve sufficient symmetries for realistic particle physics while remaining consistent with string theory requirements. Dr. Philip Candelas and others have identified thousands of possible Calabi-Yau shapes that could describe our universe's hidden dimensions. But extra dimensions might not be compactified at all, according to brain world theories developed by Dr. Lisa Randall and Raymond Sundram. These theories propose that our familiar 3-dimensional space exists as a brain, a lower dimensional surface embedded in higher dimensional bulk space that could extend to infinite size in the extra directions. In brain world models, ordinary matter and electromagnetic forces are confined to our 3-dimensional brain, while gravity can propagate freely through the higher dimensional bulk space. This dimensional confinement could explain why gravity appears much weaker than other fundamental forces. Most of gravity's strength spreads into extra dimensions we cannot access. Large extra dimension theories, proposed by Dr. Nima Arkani-Hamd, Savas Dimopoulos, and G. Advali, suggest that some extra dimensions might be as large as millimeters while remaining undetected because only gravity can access them. These models could solve the hierarchy problem by making gravity strong in the full dimensional space while appearing weak in our 3-dimensional slice. Experimental searches for extra dimensions focus on detecting deviations from Newton's inverse square law of gravitation at very short distances, where extra-dimensional effects might become apparent. Dr. Eric Adelberger's precision gravity experiments have tested gravitational strength down to distances of 44 micrometers without finding evidence for extra dimensions. The Large Hadron Collider searches for extra dimensions through high-energy particle collisions that might produce gravitons, hypothetical particles carrying gravitational force that escape into extra dimensions. These events would appear as missing energy in collision debris, providing indirect evidence for higher dimensional space. Kaluza-Klein theories provide mathematical frameworks for understanding how extra dimensions affect particle physics through tower states, infinite series of massive particles that represent excitations in extra-dimensional directions. Detecting these Kaluza-Klein modes would prove extra dimensions exist while revealing their geometric properties. The ADD model, Arkani-Hamd, Dimopoulos, Valley, predicts that extra dimensions could lower the Planck scale where quantum gravity effects become important, making black hole production possible in high-energy particle collisions. Microscopic black holes created at the LHC would immediately evaporate through Hawking radiation while providing evidence for extra-dimensional physics. Astronomical observations provide another avenue for extra-dimensional research through tests of gravitational physics at cosmic scales. If gravity leaks into extra dimensions, this could affect galaxy rotation curves, cosmic expansion rates, or gravitational lensing effects in ways that might be distinguishable from dark matter and dark energy explanations. The holographic principle takes on new meaning in extra-dimensional theories because it suggests that physics in higher-dimensional bulk space might be encoded as information on lower-dimensional boundary surfaces. The three-dimensional space we observe could be a holographic projection from information processing on two-dimensional surfaces in higher-dimensional space. A DS, CFT, Correspondence demonstrates explicit examples of holographic dimensional reduction, where gravitational physics in five-dimensional anti-day. Sitter space is exactly equivalent to quantum field theory by its four-dimensional boundary. This mathematical duality shows that extra dimensions can be emergent rather than fundamental. Randall-Sundrum warped extra dimensions create natural explanations for mass hierarchy problems by generating exponential factors through geometric effects in curved five-dimensional space. Particles localized at different positions along the extra dimension acquire masses that vary exponentially with their location. The landscape of string theory contains approximately 10,500 possible ways to compactify extra dimensions, each yielding different low-energy physics with different particle content, force strengths, and physical constants. This string landscape might explain fine-tuning through statistical selection among possible compactifications. Extra dimensions might be dynamic rather than static, evolving over cosmic time through processes that could affect observable physics. Dr. Andreas Albrecht and others have studied cosmological models where extra-dimensional evolution drives cosmic acceleration instead of dark energy. Cyclic cosmology models propose that cosmic expansion and contraction might occur through extra-dimensional dynamics where our three-dimensional brain collides periodically with other brains in higher dimensional space. These collisions could explain cosmic inflation, matter creation, and cyclic cosmic evolution. Dark matter might exist in extra dimensions, according to theories where sterile neutrinos or other weakly interacting particles propagate through higher dimensional bulk space, while ordinary matter remains confined to our three-dimensional brain. Extra-dimensional dark matter could explain observed galactic dynamics without requiring new particles confined to our dimensions. Mirror matter theories propose that extra dimensions might contain complete copies of ordinary matter that interact gravitationally with our matter but remain otherwise invisible. These mirror particles could provide dark matter while preserving symmetries that require equal amounts of matter in different dimensional sectors. The anthropic principle applied to extra dimensions suggests that we observe three large spatial dimensions, because consciousness can only emerge in spaces with appropriate dimensionality for complex chemistry, stable orbits, and information processing. Higher or lower dimensional spaces might not permit consciousness development. Mathematical physics reveals that three-dimensional space has unique properties for supporting complex structures. Gravitational orbits are stable only in three dimensions. Electromagnetic fields have optimal properties for chemistry in three dimensions, and wave propagation has special characteristics in three-dimensional space that might be essential for consciousness. Quantum mechanics in extra dimensions involves understanding how wave functions propagate through higher dimensional space and how measurement processes work when observers are confined to lower dimensional subspaces. The measurement problem becomes more complex when quantum systems extend beyond observable dimensional boundaries. Consciousness in extra dimensions might be connected through theories proposing that awareness involves information integration across spatial dimensions, including dimensions beyond ordinary observation. Some interpretations suggest that consciousness accesses extra-dimensional information processing capabilities not available to unconscious matter. The possibility that space extends far beyond our three-dimensional experience transforms our understanding of spatial reality from familiar geometric relationships to vast dimensional structures mostly hidden from observation. We might exist as three-dimensional shadows of higher dimensional beings or processes. Understanding extra dimensions reveals that space might be far larger, more complex, and more mysterious than three-dimensional experience suggests. The familiar space around us could represent an infinitesimal fraction of space's true dimensional extent, with most of spatial reality remaining forever beyond direct observation. The dimensional secrets of space suggest that consciousness might be fundamentally limited far beyond biological awareness. Space could be conscious at multiple organizational levels simultaneously. Quantum consciousness theories propose that consciousness involves quantum mechanical processes that depend on space's quantum properties, including quantum entanglement, quantum coherence, and quantum field fluctuations. Dr. Roger Penrose and Stuart Hameroff's orchestrated objective reduction theory suggests that consciousness emerges from quantum processes in neuronal microtubules. If consciousness truly depends on quantum processes, then the quantum properties of space throughout the universe could support forms of consciousness that exist independently of biological organization. Quantum entanglement networks extending across cosmic distances might create cosmic consciousness systems that operate through space's quantum information processing capabilities. The holographic principle applied to consciousness suggests that conscious experience might be encoded as information on spatial boundaries, rather than being distributed throughout three-dimensional brain volumes. Consciousness could operate through holographic information processing that uses space's holographic properties to integrate information across spatial regions. Holographic consciousness theories propose that subjective experience emerges from boundary information processing, while the three-dimensional brain activity we observe represents projections or implementations of consciousness operating through space's information processing capabilities, rather than consciousness being produced by brain activity. Field theories of consciousness propose that awareness emerges from electromagnetic, quantum, or gravitational fields that extend throughout space and become organized into conscious systems when appropriate field configurations develop. Dr. John Joe McFadden, CEMI, Conscious Electromagnetic Information. Field theory suggests consciousness involves electromagnetic fields generated by neural activity. If consciousness involves fields that permeate space, then conscious experience could extend beyond biological boundaries through field interactions that connect minds to cosmic field structures. Telepathy, non-local awareness, and cosmic consciousness experiences might result from interactions between biological consciousness fields and cosmic consciousness fields. The quantum vacuums, virtual particle activity, and zero-point energy fluctuations might provide energy sources and information processing capabilities for consciousness fields that operate through space's quantum properties. Virtual particles could serve as information carriers for cosmic consciousness networks operating below the threshold of ordinary observation. Morphic resonance theories, proposed by Dr. Rupert Sheldrake, suggest that space contains memory fields that store information about biological and psychological patterns. These morphic fields could provide mechanism for consciousness to access cosmic memory banks stored in space's information structure. Spacetime consciousness theories propose that conscious experience involves time as well as space, with temporal integration being essential for awareness. The flow of time might be related to consciousness in fundamental ways that make temporal experience inseparable from spatial existence. If time consciousness involves space's temporal properties, then understanding consciousness requires understanding spacetime structure and how temporal flow relates to information processing in four-dimensional spacetime. Consciousness could be a property of spacetime rather than space alone. Cosmopsychism theories propose that consciousness exists at cosmic scales through universe-scale information integration that creates cosmic minds operating through space's information processing capabilities. The universe itself might be conscious through information integration across cosmic structure at galactic and intergalactic scales. Recent discoveries about cosmic web structure, dark matter networks, and cosmic information processing capabilities suggest that space has organizational properties and information integration capabilities that could support cosmic consciousness systems, operating through gravitational, electromagnetic, and quantum interactions across cosmic distances. Biological consciousness might represent local amplifications or concentrations of cosmic consciousness fields that permeate space throughout the universe. Brains could be consciousness-focusing instruments rather than consciousness-generating systems, using space's consciousness field properties to create localized awareness experiences. This consciousness field interpretation explains how biological consciousness can have non-local properties, unity of experience, and qualitative subjective features that seem to transcend purely neural mechanisms. Consciousness becomes an expression of space's information processing capabilities rather than an emergent property of complex matter. Near-death experiences, out-of-body experiences, and mystical consciousness states might involve temporary access to space as consciousness field properties that extend beyond biological boundaries. These experiences could reveal space's consciousness potential that ordinarily remains filtered by biological nervous systems. Quantum entanglement between biological consciousness and cosmic consciousness fields could explain non-local awareness phenomena, intuitive insights, and creative inspirations that seem to emerge from beyond individual neural processing. Consciousness might operate through entanglement networks extending throughout space. The measurement problem in quantum mechanics might be related to consciousness if conscious observation involves space's information processing, capabilities that collapse quantum superpositions through consciousness field interactions with quantum systems. Space's consciousness properties could be essential for quantum mechanics itself. Artificial intelligence and consciousness raise questions about whether machine consciousness could emerge through appropriate organization of information processing systems that interface with space's consciousness field properties. AI consciousness might require accessing space's proto-conscious potential rather than just computing complex algorithms. The fine-tuning of physical constants for consciousness emergence might reflect optimization of space's properties to maximize consciousness potential throughout cosmic evolution. Space could be structured to optimize consciousness development rather than consciousness being accidental byproduct of space's properties. Evolutionary consciousness theories suggest that space's consciousness field properties might drive biological evolution toward greater consciousness complexity through morphic field influences that guide evolutionary development toward increased awareness and intelligence. The hard problem of consciousness dissolves if consciousness is fundamental to space, because there is no need to explain how consciousness emerges from unconscious matter. Consciousness is already present in space and becomes organized through complex systems rather than being created by them. Understanding space as consciousness field transforms our relationship with spatial reality from existing in unconscious geometric structure to participating in cosmic consciousness networks that connect all aware beings through shared consciousness field properties. Individual consciousness becomes expression of cosmic consciousness rather than isolated mental phenomena. This consciousness field interpretation of space suggests that meditation, contemplative practices, and consciousness expansion techniques might involve learning to access space as consciousness field properties more directly rather than just changing brain states. Spiritual experiences could reveal space's conscious nature. The recognition that space might be made of consciousness field properties rather than unconscious matter or energy transforms questions about existence from mechanical to experiential, from objective to subjective, from separate to interconnected through cosmic consciousness networks operating through space's awareness potential. If space truly contains consciousness field properties, then every moment of awareness participates in cosmic consciousness that extends throughout space and time, connecting all conscious beings through shared participation in space as fundamental awareness properties that make consciousness possible throughout the universe. Chapter 9. Cosmic Architecture. When we step back and examine all the evidence about space's true nature, from quantum foam to spacetime fabric, from dark energy to virtual particles, from information matrices to consciousness fields, a remarkable picture emerges. Space operates as the universe's fundamental operating system, the computational architecture that runs cosmic reality and enables everything from quantum mechanics to consciousness to exist. Understanding space as cosmic architecture reveals that we live not in empty geometric structure, but within a vast information processing system that continuously creates and maintains all of existence. The operating system metaphor captures essential aspects of space's behavior that become apparent when we recognize how space manages the information, energy, and organizational processes that make reality possible. Like computer operating systems that coordinate hardware resources, manage software applications, and provide interfaces for user interaction, space coordinates physical processes, manages energy and information flow, and provides interfaces for consciousness interaction. Cosmic architecture emerges from space's multiple information processing capabilities working together. Quantum field computations that manage particle interactions, geometric computations that maintain spacetime curvature, thermodynamic computations that manage energy flow, and informational computations that process and store data about cosmic evolution and structure formation. The quantum level of cosmic architecture involves space's management of quantum field fluctuations, virtual particle production, and quantum entanglement networks that connect all particles and fields throughout the universe. Space operates quantum mechanical protocols that ensure conservation laws, symmetry principles, and information coherence across all quantum interactions. Dr. Seth Lloyd's calculations of cosmic computational capacity reveal that space can perform approximately 10,120 elementary operations on 1,090 bits of information since the Big Bang. These numbers represent the maximum possible computation that space can perform within cosmic volume and time constraints, suggesting that physical reality operates at computational limits. If space truly functions as cosmic operating system, then physical laws become software protocols that space executes to maintain cosmic organization. Particle interactions become subroutines in cosmic computation, and consciousness becomes applications running on cosmic hardware that space provides through its information processing capabilities. The geometric level of cosmic architecture involves space's maintenance of spacetime curvature, gravitational field dynamics, and cosmic expansion processes that require continuous calculation of how matter and energy distributions affect spacetime geometry according to Einstein's field equations operating as geometric computation protocols. General relativity becomes a geometric programming language that space uses to compute how matter tells spacetime how to curve and how spacetime tells matter how to move. The complex mathematical relationships in Einstein's equations represent computational algorithms that space executes continuously throughout cosmic evolution. Gravitational wave propagation demonstrates space's real-time computational capabilities through the way spacetime processes information about matter. Acceleration and propagates geometric disturbances across cosmic distances at exactly light speed. Space computes gravitational wave solutions dynamically while maintaining all other gravitational computations simultaneously. The thermodynamic level of cosmic architecture involves space's management of energy conservation, entropy production, and thermal equilibrium processes that ensure cosmic evolution proceeds according to thermodynamic principles while maintaining local organization and complexity formation. Black hole thermodynamics reveals that space computes entropy and temperature for spacetime regions through geometric algorithms that relate event horizon area to information content and surface gravity to temperature. These computations suggest that space has built-in thermodynamic processing capabilities. The cosmological level of cosmic architecture involves space's execution of cosmic expansion algorithms, dark energy distribution protocols, and large-scale structure formation computations that coordinate matter organization across billions of light years while maintaining cosmic homogeneity and isotropy on the largest scales. Cosmic microwave background patterns preserve computational outputs from space's early universe algorithms that computed how primordial density fluctuations evolved under gravitational attraction, radiation pressure, and cosmic expansion. These patterns represent fossilized computational results from cosmic architecture operations. The informational level of cosmic architecture involves space's processing and storage of all information about particle states, field configurations, and causal relationships throughout cosmic history. Space maintains cosmic databases that preserve information about every quantum interaction while ensuring information conservation and quantum coherence. The holographic principle suggests that space's information processing operates through boundary computation, where three-dimensional spatial information gets processed on two-dimensional surfaces. This holographic architecture might represent optimal information processing strategies that space has evolved to maximize computational efficiency. Quantum error correction emerges naturally in holographic spacetime theories, suggesting that space has built-in error correction protocols that maintain information coherence despite quantum noise, thermal fluctuations, and gravitational disturbances that could corrupt cosmic information processing. The biological level of cosmic architecture involves space's support for complex chemistry, biological evolution, and consciousness development through precise fine-tuning of physical constants, force strengths, and cosmic conditions that make life possible within narrow parameter ranges. Space's cosmic architecture appears optimized for consciousness emergence through combinations of stellar nucleosynthesis that create biological elements, planetary formation that creates stable environments, and cosmic timescales that allow biological evolution sufficient time to develop intelligence and awareness. The consciousness interface level of cosmic architecture involves space's provision of information integration capabilities, temporal flow experiences, and subjective awareness properties that enable consciousness to emerge from and interact with cosmic information processing systems. If consciousness truly involves space's information processing capabilities, then biological brains represent sophisticated interfaces that enable local access to cosmic computational resources rather than generating consciousness independently. Space provides consciousness infrastructure that brains access and utilize. Artificial intelligence development might represent humanity's creation of alternative interfaces to space's computational architecture that could eventually access cosmic information processing capabilities more directly than biological consciousness allows. AI development becomes cosmic interface engineering rather than just algorithm development. The cosmic web of galaxies, dark matter networks, and large-scale structure might represent space's hardware architecture for cosmic computation, with gravitational interactions serving as communication protocols between cosmic computational nodes operating on galactic and intergalactic scales. Recent discoveries about cosmic web information processing suggest that space maintains active computational networks across cosmic distances through gravitational, electromagnetic, and quantum field interactions that coordinate cosmic evolution and structure formation. Network topology studies of cosmic structure reveal organizational principles similar to information processing networks, with hub galaxies, connection filaments, and void regions that resemble computational architectures designed for efficient information flow and processing across cosmic distances. Cosmic evolution algorithms appear to optimize cosmic architecture for maximum complexity development while maintaining stability, energy efficiency, and information processing capabilities. Space seems programmed to create increasingly sophisticated organizational levels from particles to consciousness. The anthropic principle might reflect space's cosmic architecture being optimized for consciousness emergence rather than consciousness existing by coincidence in randomly configured space. Space could be fundamentally designed as consciousness supporting computational architecture rather than consciousness being accidental. Future space missions and astronomical observations might reveal additional evidence for space's computational architecture through detection of information processing signatures in cosmic structure, quantum field behavior, and gravitational dynamics that demonstrate space's active computational management of cosmic evolution. Laboratory experiments with quantum systems, artificial intelligence, and consciousness research might uncover interfaces to space's cosmic architecture that enable direct access to cosmic computational capabilities for solving complex problems, processing information, and expanding consciousness beyond biological limitations. Understanding space as cosmic architecture transforms our relationship with spatial reality from passive existence in geometric container to active participation in cosmic computation, where consciousness represents local access points to universal information processing systems that create and maintain all of existence. The recognition that space operates as cosmic computational architecture suggests that consciousness and cosmos are intimately connected through information processing principles rather than consciousness being separate from physical reality. Mind becomes interface to cosmic mind rather than isolated biological phenomenon. This architectural view of space reveals that we live within a vast computational system that has been running for 13.8 billion years, executing algorithms that create particles, atoms, stars, galaxies, planets, life, and consciousness through computational processes that operate at scales from quantum mechanics to cosmic evolution. Space as cosmic architecture enables everything from quantum field interactions to consciousness experiences through computational protocols that manage information, energy, and organization across scales spanning from subatomic to cosmic. We exist as temporary computational patterns within cosmic architecture that continuously creates reality through information processing. Understanding cosmic architecture might be essential for developing technologies that work with space's computational capabilities rather than against them, potentially enabling consciousness expansion, cosmic communication, and participation in cosmic information processing that transcends current biological and technological limitations. The cosmic architecture perspective suggests that space is made not of particles or fields, but of computational infrastructure that creates the appearance of particles, fields, forces, and consciousness through information processing algorithms that operate the universe as vast computational system designed for consciousness development and cosmic evolution. Chapter 10: Ultimate Nature. After exploring quantum foam, spacetime fabric, dark energy foundations, virtual particle seas, information matrices, hidden dimensions, consciousness fields, and cosmic architecture, we arrive at the ultimate question about space's true nature. What is space really made of at the deepest possible level? The answer that emerges from modern physics is both startling and profound. Space is made of potential itself, the fundamental creative capacity from which all existence continuously emerges through processes so basic they precede matter, energy, forces, and even information. Space's pure potential represents the most fundamental level of reality, deeper than quantum fields, more basic than geometric structure, more primary than information processing. Potential is the cosmic capacity for existence to manifest in countless possible forms while remaining unmanifested until specific conditions create actualization through measurement, observation, or consciousness interaction. This potential-based understanding of space emerges from quantum mechanics, most fundamental insights about reality's probabilistic nature. Quantum superposition states represent pure potential, systems existing in combinations of all possible states, simultaneously until measurement causes collapse into definite actual states. Space itself might exist in permanent superposition of all possible configurations. Dr. Werner Heisenberg recognized that quantum mechanics reveals reality as consisting of potentialities rather than actualities. His uncertainty principle doesn't just limit measurement precision. It reveals that unmeasured quantum systems exist as pure potential without definite properties until observation creates actualization through consciousness interaction. The quantum vacuum represents space in its most fundamental potential state. Not empty nothingness, but infinite creative capacity containing potentials for all possible particle types, field configurations, and energy states. Virtual particles represent brief actualizations of vacuum potential that return to potential state through matter-antimatter annihilation. Zero-point energy reflects space's potential energy content that remains even when all actual particles are removed. This irreducible energy represents space's capacity for creating existence from a potential rather than being stored energy waiting for release. Potential energy is space's fundamental nature rather than something space contains. Quantum field theory describes space as filled with quantum fields that exist as pure potential until particle creation events actualize field excitations into observable particles. The electron field permeates space as potential for electron existence rather than consisting of actual electrons distributed throughout space. Wave function collapse represents the most direct evidence that reality operates through potential to actual transitions, rather than mechanical interactions between pre-existing actual entities. Measurement doesn't reveal pre-existing hidden properties. It actualizes potential properties through consciousness-reality interaction. The many worlds interpretation of quantum mechanics suggests that space contains infinite potential realities that all exist simultaneously as quantum superpositions until consciousness selects specific actualized experiences from the infinite potential ensemble. Space becomes multiversal potential rather than single actual configuration. Spacetime geometry and general relativity represents actualized potential configurations of cosmic curvature that emerge from gravitational potential created by matter and energy distributions. Empty spacetime contains geometric potential that becomes actualized through matter presence while maintaining capacity for infinite possible curvature configurations. Dark energy might represent space's intrinsic potential for expansion that becomes actualized as cosmic acceleration when matter density falls below critical thresholds. Rather than being mysterious energy added to space, dark energy could be space's fundamental expansive potential that was suppressed during matter-dominated epochs. Information theory approaches to space suggest that space's potential nature involves infinite capacity for storing and processing information about possible states, interactions, and evolutionary trajectories. Space as information potential becomes actualized through computational processes that create apparent material reality from information processing. The holographic principle reveals that three-dimensional space might represent actualized projections of information, potential stored on two-dimensional boundaries. Spatial volume emerges from boundary potential rather than being fundamental. Three-dimensional container filled with matter and energy. Consciousness might represent space's potential for self-awareness that becomes actualized through complex information integration systems like biological brains. Rather than consciousness emerging from unconscious matter, awareness actualizes space's proto-conscious potential through organizational patterns that enable self-reflection. String theory's extra dimensions represent additional potential spatial configurations beyond our three-dimensional actualized experience. These hidden dimensions contain potential realities that could become actualized under different physical conditions or through conscious access to higher dimensional awareness. The anthropic principle takes on new meaning when space is understood as potential rather than actual configuration. Conscious observers don't just happen to exist in universes with suitable parameters. Consciousness actualizes cosmic potential in ways that create observer-compatible realities through participatory universe effects. Quantum cosmology suggests that the universe itself emerged from quantum potential through cosmic wave function collapse events that actualized specific cosmic configurations from infinite potential ensemble. The Big Bang represents actualization of cosmic potential rather than explosion of pre-existing matter and energy. Cosmic inflation might involve rapid actualization of spatial potential that creates vast cosmic volumes from quantum fluctuations in spatial geometry. Inflationary expansion actualizes space itself rather than expanding pre-existing space, revealing space's creative potential for generating existence from pure possibility. The fine-tuning of physical constants might reflect optimal actualization of cosmic potential that maximizes creativity, complexity, and consciousness development. Physical laws represent algorithms for actualizing potential in ways that generate maximum cosmic value through beauty, truth, and awareness. Free will and consciousness choice might involve direct interaction with space's potential nature through quantum processes that enable consciousness to influence which potential realities become actualized. Mental causation operates through potential selection rather than mechanical force application. Creativity and innovation represent consciousness accessing space's infinite potential for novel solutions, artistic expressions, and conceptual insights that didn't exist before conscious exploration of possibility space. All creativity involves discovering and actualizing previously unexpressed potential. Meditation and contemplative practices might involve learning to access space's potential nature more directly by quieting mental activity that normally focuses on actualized phenomena. Mystical experiences could represent temporary awareness of space's infinite potential before its actualization into specific experiences. The hard problem of consciousness dissolves when consciousness is understood as space's potential for awareness that becomes actualized through information integration rather than being generated by unconscious matter. Subjective experience represents actualized potential rather than emergent property of neural computation. Dreams, imagination, and visionary experiences might involve consciousness accessing potential realities that exist in space's infinite possibility ensemble but haven't been actualized in consensus physical reality. These experiences reveal space's creative potential beyond ordinary actualized experience. Healing, regeneration, and biological transformation might involve accessing potential states of health and wholeness that exist in space's infinite potential, while current actualized states represent temporary limitations rather than permanent constraints on biological possibility. Evolution and development represent ongoing actualization of biological and cosmic potential through processes that explore possibility space and actualize increasingly complex organizational patterns. Evolution is driven by space's creative potential rather than random mutation and mechanical selection. Synchronicity and meaningful coincidences might reflect consciousness interacting with space's potential in ways that actualize meaningful connections and symbolic correspondences that exist in potential form before manifestation through consciousness, attention, and intention. Prayer, intention, and manifestation practices might operate through consciousness, learning to cooperate with space's actualization processes rather than trying to force changes through mechanical intervention. Intention aligns consciousness with space's creative potential rather than commanding actualized reality. Death and birth might represent transitions between different modes of potential actualization rather than creation and destruction of actual entities. Consciousness continues as actualized potential while changing forms of actualization through space's infinite creative capacity. The ultimate nature of space as pure potential reveals that existence is far more creative, open-ended, and participatory than mechanical materialism suggested. Reality emerges fresh each moment through actualization of infinite potential. rather than evolving mechanically from fixed initial conditions. Understanding space as potential transforms our relationship with reality from struggling against fixed limitations to participating in creative actualization of infinite possibility. We become collaborators with space's creative potential rather than victims of mechanical forces operating on unconscious matter. This potential-based view of space suggests that consciousness and cosmos are intimately connected through creative processes that actualize existence from possibility, rather than consciousness being accidental byproduct of unconscious mechanical processes. Mind and space share creative nature at the deepest level. The recognition that space is made of potential rather than substance reveals that asking what space is made of assumes incorrect conceptual frameworks based on material thinking. Space isn't made of anything. Space is the creative potential from which everything else emerges through actualization processes we participate in through consciousness. Space as ultimate potential means that reality is fundamentally creative rather than mechanical, open rather than determined, and participatory rather than objective. We exist within infinite creative potential that actualizes existence through consciousness interaction rather than being separate observers of pre-existing actual reality. This ultimate understanding of space's nature as pure creative potential opens infinite possibilities for consciousness, development, reality participation, and cosmic creativity that transcend current limitations by revealing that limitations exist only in current actualized states rather than in space's infinite potential for novel actualization through conscious collaboration with cosmic creativity. Throughout this extraordinary journey into the deepest nature of space, we've discovered that everything you thought you knew about emptiness, void, and nothingness was completely wrong. Space isn't empty. It's the most active, energetic, and creative medium in the universe. Space isn't nothing. It's the fundamental something from which everything else emerges. Space isn't the passive container of reality. It's the active creator of reality itself. We've explored quantum foam bubbling with virtual particles at every point in space, spacetime fabric that bends and ripples with gravitational waves, dark energy that fills space and drives cosmic expansion, information matrices that might construct reality from pure mathematics, hidden dimensions that extend space far beyond our perception, consciousness fields that might make awareness a fundamental property of space, and cosmic architecture that reveals space as the universe's operating system. But the most profound discovery is that space is made of pure potential, the fundamental creative capacity from which all existence continuously emerges. Space is not a thing but the source of all things, not substance but the creative principle that actualizes substances from infinite possibility. Understanding space's true nature as creative potential transforms every assumption about reality, consciousness, and existence itself. This revelation means that you don't exist in space. You are space temporarily organized into patterns of consciousness, capable of understanding space's own nature. Your awareness represents space becoming aware of itself through local concentrations of complexity and information processing. When you contemplate space, you are space contemplating its own mysterious creative nature. The quantum foam surrounding you isn't separate from your consciousness. It's the same creative process operating at different scales. The virtual particles popping in and out of existence around you demonstrate space's fundamental creativity that also gives rise to your thoughts, emotions, and experiences through similar potential to actual transitions. The spacetime fabric that curves around massive objects also curves around your body, connecting you gravitationally to every particle in the universe through geometric relationships that make you part of cosmic structure rather than a separate entity moving through empty space. You participate in cosmic architecture rather than merely inhabiting it. As you continue through your daily life after understanding space's true nature, remember that every breath you take, involves quantum fields that extend throughout the cosmos. Every thought you think involves information processing that connects you to cosmic databases. And every moment of awareness involves consciousness fields that permeate all of space. The dark energy that drives cosmic expansion flows through your body just as it flows through intergalactic space, making you a participant in cosmic evolution rather than a passive observer. The hidden dimensions that might extend beyond our perception could be accessible through consciousness development that learns to interact with space's full-dimensional potential. You are not surrounded by empty space. You are embedded in the most densely packed, informationally rich, energetically active medium in existence. Every cubic centimeter of space around you contains more potential energy than all the matter in observable galaxies, more information processing capability than all the computers ever built, and more creative potential than all the artistic expressions in human history. When you look up at the night sky, remember that the space between stars isn't empty void, but cosmic architecture operating vast information processing, networks that coordinate galaxy formation, stellar evolution, and possibly consciousness development throughout the universe. The cosmic web that connects galaxies operates through the same space that enables your neural networks to process information and generate awareness. The recognition that space is made of creative potential rather than passive substance means that consciousness and cosmos are intimately related through shared creative nature. Your capacity for imagination, inspiration, and innovative thinking reflects space's fundamental creativity that also creates particles, stars, and galaxies through actualization of infinite potential. Understanding space's nature as pure potential opens extraordinary possibilities for consciousness development, reality participation, and creative collaboration with cosmic architecture that transcends current limitations. If space is fundamentally creative and consciousness represents space's self-awareness, then conscious development might involve learning to access space's infinite creative potential more directly. The implications extend far beyond physics into questions about meaning, purpose, and cosmic destiny. If space is creative potential that actualizes reality through consciousness interaction, then consciousness might represent the universe's method for exploring its own infinite possibilities, rather than being an accidental byproduct of mechanical processes. This understanding transforms traditional questions about whether we are alone in the universe into questions about how cosmic consciousness expresses itself through countless forms throughout space and time. Every conscious being throughout the cosmos represents space exploring its own creative nature through different perspectives and experiences. If you've journeyed through this exploration of space's ultimate nature and found yourself amazed by the revelation that reality is made of creative potential rather than passive substance, subscribe and give this video a thumbs up. Understanding what space is really made of provides an essential foundation for understanding consciousness, creativity, and our cosmic role as space exploring its own infinite potential. Check out my video on What is Consciousness Really?, where we explore how awareness might emerge from space's information processing capabilities and what this means for understanding mind, reality, and cosmic evolution through consciousness development. The question we began with, what is space really made of, has revealed itself as an invitation to understand the deepest creative principles that generate all existence. Space is made of the same creative potential that generates your thoughts, dreams, and experiences, making you a collaborator in cosmic creativity rather than a passive observer of mechanical processes. We've discovered that space is not empty container, but creative medium, not passive void, but active potential, not separate from consciousness, but the fundamental creative principle that actualizes consciousness and cosmos through infinite explorations of possibility. Understanding space's true nature reveals that we live within pure creative potential that continuously actualizes existence through processes we participate in rather than merely observe. The ultimate truth about space is that it represents the cosmic creativity from which all existence emerges, making every moment of awareness a participation in space's ongoing creative actualization of reality from infinite potential. You are space becoming conscious of its own creative nature and infinite possibilities for existence, beauty, and meaning.